So, hello everyone. I'm Tanjali Jaina. I'm a PhD scholar from IIT Delhi. So, I'm also a PMRFTA for this course, where I will be going through all the concepts, all the weekly concepts that has been taught during the following week. And besides that, I will try to solve the doubts or clarify the doubts that you must be having for the weekly assignment. And besides going through the weekly concept, we'll see a few additional problems. So we'll solve few additional problems that will help you to understand the concept better, as well as that will help you to helpful for you to during the problem solving. So without further delay, let us start our session. So this in this week, we primarily see what are the different kinds of laser that has been discussed till now. So we have gone through the first laser that has been proposed by the scientist, as well as we see various advanced laser system that has been used till now for various applications. Let us see what are the story of laser discovery. So, so in 1958, the theory of laser action was given by the student by two scientists independently. So, scientists of Townsend, Solow, and Nikolai Basov, and follow scientists. They have proposed what are the theory of laser action, and the first working laser it was proposed in 1960, which is Ruby laser, proposed by Mayman and House Research Laboratory. So it will delay in the way I'm speaking and the way the screen responds because of the internet issue. So please bear with me. Uh, okay. So the first laser that has been proposed is the Ruby laser. And the second one, which was proposed in 1961, is helium neon laser by Alizaga Neval in Bell's laboratory. And in the neodymium calcium WO4 laser in Johnson and Nassau laboratory. And the next laser that was proposed in 1962 is the semiconductor laser around wavelength 0.87 micrometer by four independent groups. In 1963, the CO2 laser it was proposed, which is wavelength around 10.6 micrometer in Bell's lab by KCK and Patel. And in 1964, the argon ion laser, which is wavelength around 514.5 nanometer by Bridges and Hawkes Research Laboratory, and NDF laser, which is wavelength around 1064 nanometer. So let us see what are the different types of lasers. So lasers are classified based on the types of active medium they have. So the active medium can be a liquid, so in liquid lasers, or it can be a semiconductor in some semiconductor laser. So the first, let us see the first one. The first one is the gas laser. So gas laser, it's say helium neon laser, argon ion laser, CO2 and N2 laser. And in this laser, primarily we use different types of atoms, such as helium in helium neon laser, to excite the active medium. So these helium atoms, these are excited by electric discharge. Okay. And the second one is the solid state laser, which is one is ruby laser, NdAr laser, titanium sapphire laser, and fiber laser, where optical pumping it is done by flash lamps and diode laser. And liquid laser, as I've said earlier, so liquid medium acts as active medium for the living action. So the examples are rhodamine 60 and stilbene 420. Optical pumping, it is given by Stilbene. Yes. And the next one is the semiconductor laser, which is aluminum gallium arsenide junction, India's ASAP or indium phosphide based double lateral structure PN die. So, and we have seen earlier also the pumping in semiconductor laser. It is done by changing the injection current through the forward bias PN junction. So, go through some of the laser in our next few slides. So, the first one is the helium laser, which, as we have seen earlier, it's a four-level system. So, if you see the diagram, the left one is for the energy diagram for the helium atoms, and the right figure, it is the energy diagram of the neon atom. So, if you compare this energy level, you can see some of the energy levels of the neon atoms and helium this atom is excited, then the atoms can resonantly transfer the energy to the neon atom. Okay. So, in helium neon laser, the active medium is the neon atom. So, the whatever lasing we see, whatever lasing action is done, it is due to the excited neon atoms from the metastable state to the ground state. And the helium atom, these are used to indirectly excite the neon atom so that they can get excited to the higher energy level and get populated in the metastable state. So, as I've said earlier, helium atoms, these are used to excite the neon atoms. So, if you see the left figure, helium atoms these are excited by the excitation. These are excited by discharge. So, after application of a discharge, the new helium atoms will get excited to the higher excited state. And as the helium and neon atoms, they have same energy level. So energy level almost coincide with each other. So that means the helium atoms can resonantly transfer the energy to the neon atoms. So neon atoms get excited from the 4s to 5s level. And from the 5s level, it goes to the metastable, so 5s level, it's a metastable state. Okay. So from this level, it can come either to the 4p level by emitting a wavelength around 3.39 micrometer, or it can come to the 3p level where the energy is emitted with a wavelength of 0.6328 micrometer. So whatever helium neon laser we use in the laboratory, it's primarily of 632.8 micrometer. So we see this wavelength during the experiment. Other wavelengths can be used for other application. And other type of excitation that can lead to a wavelength emission is from 4s to 3b level, which emits a wavelength around 1.5 to 1.523 micrometer. So if you see, so the de-excitation occurs from the 3p level, and the de-excitation, it is facilitated mainly through collision with the walls. So we will see later that in the configuration of helium neon laser, the walls are very thin so that the neon atoms can collide with the walls and get de-excited to the ground state. Okay. And there are several other wavelengths at which lasing is possible, as we have seen earlier, as we have seen now also. Helium neon laser can emit at various wavelengths 3.39, 0.6328, and 1.523. So these different types of wavelength is possible for lasing action. And by using a frequency selective feedback mechanism, we can filter out the different wavelengths. Okay. So Next, we'll see the schematic of a helium neon laser. So this is the schematic of the helium neon laser. So if you see, there are two mirrors, mirror M1 and mirror M2. Uh, and there is a, so mirror M1 is reflectivity of 97% and mirror M2 has reflectivity of 99%. And the laser mainly comes through the mirror M1. Okay. And if you see, a voltage is applied so that the helium atoms get excited to the higher energy level and they can resonantly transfer the energy to the neon atoms. Okay. And the voltage that is required is around 1.1 to 4 kilo volt. And besides that, you can see the diameter of this tube. It is around 2 to 5 micrometer. 2 to 5 millimeter. So this is used to de-excite the neon atoms so that the excited neon atoms, when they collide with the wall, they get de-excited to the ground state. So this is the main purpose of using a thin, small diameter wall in the helium neon laser. And the concentration ratio is it is around 10 is to 1 by volume. So if you have 10 helium atoms, then we mix one volume of neon atom. And as we have seen, helium atom, it is used to pump the neon atoms by collision, and the lasing transition are mainly from the neon atom. Okay. So next we'll see some of the common solid state laser. So the first one is ruby laser, which is a chromium dope aluminum oxide, and the wavelength it is around 0.6943 micrometer, and which is a lifetime of 3 millisecond and efficiency of 0.1 percentage. Okay. And the next one is Nd:YAG laser, which is where lamp is used to excite the active medium. And the wavelength is around 1.064 micrometer, which is a wavelength, which is a lifetime of 230 microsecond and a efficiency of 5%. So the next solid state laser, it's neodymium yttrium vanadate, which is wavelength around India only 1.064 micrometer. But the lifetime is different here. It's 100 microsecond and the efficiency is also two times of India's laser, which is around 10%. And ND glass, the wavelength of when the lasing action is done, it is 1.053 micrometer, and the lifetime is 370 microsecond with a efficiency of 1%. So the next solid state laser, it's ytterbium doped in YAG, which emits wavelength around 1.030 micrometer, and it has a lifetime of 1 millisecond and a efficiency of 5%. The next one is the titanium sapphire laser, which we'll see it is a tunable laser, and the wavelength, the lasing wavelength can be tuned from 0.7 to 1.1 micrometer. So it's a tunable laser, and it is a lifetime of 3.9 microsecond and efficiency of 0.01%. The fiber laser that we'll see, one is the erbium doped silica, where erbium atoms is used to make the lasing action in the silica matrix. And the wavelength is typically it ranges from 1.35 to 1.65 micrometer, and it is a lifetime of 10 millisecond and efficiency of 15%. And the next fiber laser is ytterbium doped in silica. So this is used for high power laser. So when you want high power laser, we either use this, and we'll see other methods to get high power laser. And for ytterbium in silica, the wavelength is around 1.01 to 1.09 micrometer. The lifetime is 1 millisecond and it is high efficiency of 30%. So these are some common examples of solid state laser and some information about them. So the next we'll see is the Nd:YAG laser, where we have seen the flash lamp is used to excite the active medium. So if you see the energy level diagram, so let us see the schematic of the laser system first, which is this one. So it consists of mirror M1 and mirror M2, which is reflectivity of 98 and 99%. And flash lamp is used to excite the Nd:YAG rod. And the whatever laser build up inside the cavity, it passes through mirror M1. Okay. And for lasing action to happen, what we need the flash lamp, which should be provided a voltage of around 1 kilowatt. So in the order of kilowatt. So that is why to cool the flash lamp, we use cold water system so that the lamp don't get heated while uh, now during the lasing action. And but the length of this active medium typically it is in the order of 10 to 15 centimeter, and the mirror M1 M2 separation it is in the order of 1 to 2 meter. So if you see the energy level diagram, so there are excitation that can happen from the ground state to the higher excited state. That is from the 4I9 by 2 ground state to the 4F7 by 2 excited state. And from this excited state, either 4F7 by 2 or 4H9 by 2, the atoms can be excited to the metastable state, which is 4F3 by 2. This is the metastable state where the lifetime is a little longer, and the population, the atoms, it's relatively stay here for a longer interval of time because it doesn't follow the selection rule. So, as we have seen from the excited state, the atoms get de-excited through first non-radiative transition, and from this 4F3 by 2, whenever we provide a radiation of 1.06 micrometer, the atoms will get de-excited to 4I11 by 2, and from this level 2 will get de-excited to the ground state. Okay. So this is the schematic of energy level diagram of Nd:YAG laser, which is operated through a flash lamp. So the next laser system is the diode pumped Nd:YAG laser. So if you see the schematic of diode pumped solid state laser, so it consists of a laser diode which emits wavelength around 800 nanometer. And this wavelength is focused to the cavity, which is made up of a active medium as well as a dichroic mirror. So dichroic mirror, these are multi-layered dielectric mirrors. So there are different layers of dielectric, which and the thickness and wavelength of this multi-layered dielectric mirror are such that it is this dichroic mirror, it is highly reflective at the wavelength at which the lasing action is happening, like 10 around 1064 nanometer. So for this, where the lasing action is happening, this mirror is highly reflective. It doesn't allow the transmission of the lasing wavelength other than at the other mirror where this mirror where 10% of this 1064 nanometer laser wavelength will be passed through the dichroic mirror. And this mirror, it is also the specialty of this mirrors is it is highly transmitted for the pumping wavelength. So it is 800 nanometer where we are this 800 nanometer we are using this for the pump. to pump the laser medium, the active medium. So this for this wavelength 800 nanometer, this dichroic mirror is highly transmitted. So whenever this from the source laser diode, when this wavelength get focused to the dichroic mirror, so it will easily pass through this dichroic mirror because these are highly transmitted for the 800 nanometer wavelength. But for the laser wavelength, which is around 1064, these mirrors are highly reflective. If you see, the first mirror is around 98% reflective for the uh, laser wavelength 1064 micrometer, and the second mirror is around 90% reflective for the 1064 nanometer. Okay, and so other 10% it will pass through the dichroic mirror, and for the DPSS laser, that is diode pumped solid state laser, the overall efficiency is around 10%. Okay, so let us see the next part. So this we have seen earlier during while studying the ray paths in different types of mirror resonator. So inside a spherical mirror resonator, so the whatever the wavelength that is getting built up inside this cavity, it the beams look like say Gaussian beads which moves back and forth inside this two mirrors M1 and M2. The next one is the DPSS with a intracavity crystal for single harmonic generation. Okay. Uh, so single harmonic generation, it's like it's a nonlinear phenomena. So SSG, that is mhm. So SSG, it's a single harmonic generation. It's a nonlinear phenomena. Mhm. So if you see the intracavity, inside the two mirrors, M1 and M2, the intensity of the laser beam is much higher than the intensity of the laser beam outside the cavity. So if you put a crystal here, yeah, if you put a non-linear crystal here, so what will happen because of the higher intensity of the laser beam inside the cavity, we'll see non-linear phenomena that can be excited inside the non-linear crystal. So one of these non-linear phenomena is single harmonic generation, where if you put let's say a wavelength around omega, so we'll get the response around 2 omega. Or in terms of wavelength, if it is lambda, then you will see a response around lambda by 2. So it is basically the single harmonic generation process. So if you see the schematic, so it is similar to the diode pump solid state laser, where we use the diode laser around 800 nanometer and we focus it to the dichroic mirror. And because of the high intensity of light inside this cavity, inside this dichroic mirror in this region, what will happen? So besides, so earlier we'll see the lasing action around 1064 nanometer or around 1.06 micrometer. And because now, in addition to the active medium, which is Nd:Arc laser rod, we have placed a nonlinear crystal here. So that is why, besides this 1064 nanometer lasing wavelength, we'll see a response around 530 nanometer also. So this is because of the nonlinear process, which is single harmonic generation, that is being excited inside this nonlinear crystal. So here you can see we'll see a two outputs. One is around the laser wavelength, which is 1064 nanometer, and other is around 532 nanometer. The next one is the exfolded cavity and crystal for the single harmonic generation. So exfold cavity, the main purpose is to make the device more compact. So what happens many times, we require different components to be integrated inside the laser system. So for that case, if you see a linear one, if you use a linear one, then that will increase the length of this, that will increase the design overall dimension of the laser system. So for that case, when you want higher integration of optical component, we use exfold cavity, where you can see it's similar to the diode pumped solid state laser, where we use dichroic mirror M1 and M2 in both sides. Dichroic mirror. 1 minute. So in this wavelength, if you see the sorry, this line, this is the laser wavelength. It is around 1064 micrometer, and we have used a nonlinear crystal, LBO, which is a nonlinear crystal, which can get a response around 532 nanometer. We can get a response around 532 nanometer. Besides that, we can also integrate isolator, which the main purpose of using the isolator is to pass the light in one direction only. So it blocks the other path of the light. So only one, like let's say forward direction is allowed and the backward direction is blocked by this isolator. So using this X4 cavity, we can integrate different optical component inside the laser system. So in between, if you have any doubt in any of the slides, so please feel free to stop me at that time, or you can write down your query in the chat box, or you can unmute yourself also. Okay. So let us see what is the next one. So next one is the titanium sapphire laser, which as we have seen, it's a tunable laser. So the tunability, it is mainly because of the birefringent tuner that we use inside the exfold cavity. If you see, it also consists of mirror M1, mirror M2, and one optical isolator, which allow the light to propagate in one direction and block the backward direction propagation of light. And besides that, so the active medium is the titanium sapphire crystal. Besides that, what you use, we use a birefringent tuner. So birefringent tuner, it's made up of a stack of birefringent material. So inside this birefringent material, different phase difference are created. So depending on the phase difference, we can choose and we can tune the lasering wavelength inside the active medium. So we'll see in the next slide in details. And it allows, if you remember, it is used to select a single longitudinal modes inside the cavity if we have many. Okay. And using this birefringent tuner, we can tune the wavelength from 700 nanometer to 1100 nanometer. Okay. 1 minute. So there is a trick. Okay. So, okay. So let me tell you in detail about what is the birefringent material. So birefringent materials, these are made up of stack of different birefringent material. So what we so let us take one birefringent material. So what will happen? It is two refractive index. One is N0, one is Ne. So N0 means refractive index of ordinary ray, and N is refractive index of extraordinary ray. So whenever you launch a light in, let's say, in this direction, so you can decompose this light, you can decompose the polarization in this direction and one in this direction. One is along NE, one is along NZ. And what happens in the birefringent, these different components, they travel at different speed. So because of some material properties, these uh, perpendicular component, they travel at different speed. So because of the different speed and different group velocity of this different component, what we'll see a phase difference which is given by 2 pi by lambda n0 minus Ne into d. So you can see this phase difference depends on the refractive index as well as the what is the thickness of the birefringent material. Okay. So by appropriately choosing what is the uh, different plate thickness and what is the orientation angle of this birefringent material, we can tune the laser wavelength. So we see there are different laser wavelength that is allowed by this birefringent material. But by selectively orienting the birefringent material and by selectively choosing the different thickness of the material, we can make the laser, we can make certain modes of the laser to get build up inside the cavity and other modes not build up inside the cavity. And how can you choose one of these longitudinal modes? So using it along, you can choose one of the longitudinal mode to pass through the mirror, other mirror. Okay, this we have seen earlier. So this is one of the tunable laser. The next one is the MOPA configuration. So MOPA means master oscillator power amplifier. So it happens. Please provide lecture slides on week 9 onwards. Okay. So I think I have uploaded few of the lecture slide in the Google Drive. If not, so let me see up to how many I have. So I think I have uploaded 4, 5, 6, 7. I've uploaded in the Google Drive. Okay. So okay, I will today I will upload the next one. Like from 8, 9, 10, 11, I will upload the lecture slides. Okay. So by today, I will upload all the lecture slides which you want. Okay. Okay. So let us move to our the concept that we're seeing. So for high power laser, so if you want a high power laser, what we can do? We can build up the laser intensity inside the laser cavity and we'll pass through this laser output through a power amplifier so that the laser get amplified inside this power amplifier and we'll see amplified output in the output of the power amplifier. So what happens in the power amplifier? The population inversion will get higher and higher when you pass through the laser wavelength. So because of the higher population inversion, we'll see amplified output in the output of the power amplifier. So, and if you see the amplifier output, the ends of this power amplifier is anti-reflection coated so that doesn't transmit. So whatever laser it get inside to the power amplifier, it doesn't leak to the laser cavity. Okay. Um, So frequency selective mechanism. So as the name indicate, it is used to select few frequency over the lasing frequency. So it's like, as we've seen in helium neon laser, if you recall, there are various wavelength at which it can give the laser wavelength. So it can various laser wavelength can oscillate inside the laser cavity. So to choose certain frequency in the output, what you can do, you can choose either the active mode. You can choose active means to select some frequency, or you can choose the passive mode to select few frequency. So in active mode, as we have seen, we use electro-optic modulator or acousto-optic tunable filter, where we see that there is a phase modulation that will happen inside the electro-optic modulator whenever there is a RF that is being injected to this electro-optic crystal. So this phase modulation, it's finally translated to the intensity modulation. And if you see the relation, the fundamental relation between the phase difference and the uh, path length. So phase difference, it is given by K0 delta in L. K0 is the free space wavelength, free space wave vector, which is equal to 2 pi by lambda. Delta n is the refractive index difference and L is the path length. So you can see del phi it is related to lambda. So depending on different wavelength, we'll see different phase difference. So by introducing different phase difference, we can select different wavelength from the cavity. In the passive mode, we use either external cavity grating or prism mirror combination or birefringent filter to select few frequency from the laser cavity. Okay. So if you see the external cavity grating, if you see this figure, so the mirror M2, it is replaced by a reflection grating. So similarly, as we have seen, when you have a grating and when you incident one laser beam or any source, any light source in this direction, so light get diffracted in different direction. Other than the transmitted light, we'll see light getting diffracted in other direction. So we say this is first order diffraction, second order diffraction. This is also first order diffraction, second order diffraction, and it is the transmitted light is the zeroth order. Okay, and by making this different diffraction order, you can make certain order of light to escape the laser cavity. So other than this zeroth order mode, all other mode will get escaped out of this cavity. Okay, and this order mode depends on the wavelength. So different order, first and second or zeroth order depends on the wavelength of light. If you recall, this is the Bragg's law, n lambda equal to 2d sine theta. So theta it depends on the lambda. So depending on the angle, so we can filter out different wavelength. So what we do in the external cavity? So we use a reflection grating. So instead of a transmission grating, we use reflection grating where light will be get reflected in different direction. So if you see this figure, so this mirror, this grating is tilted at one angle. So depending on the angle, some wavelength will get reflected in this direction, some will get reflected in this direction. When this wavelength of light, which is getting diffracted in certain angle, this will not be get built up inside the cavity because it is escaping. It is escaping out of the cavity. Only the modes that is the wavelength that is directly reflected in this direction. Let me take a different color. So in this direction, it will be get built up inside the cavity. So by using a reflection grating, you can choose certain wavelength to build up inside the cavity. And what we can do also, we can use a prism mirror combination and also a birefringent filter to select few frequency to build up inside the cavity. So let us see what is the prism mirror configuration. So inside the cavity, we have a prism. So if you recall prism, whenever you incident a white light in the prism, we'll see a dispersion of light. So different wavelength of light get diffracted in different angles. Okay. So these angles of this diffracted light in different angle, they correspond to different wavelength of light. Let's say lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, etc. And by using a tilted mirror M1, sorry M2, we can choose a wavelength to get reflected in this direction so that it get build up inside the cavity and other wavelength to escape out of this cavity. Okay. So by dispersing the light through the prism and by using a tilted mirror M2, you can choose what frequency to build up inside the cavity. And similarly, we have seen what are the birefringent tuners. So it is made up of a stack of materials, birefringent materials with a varying thickness. So depending on the thickness, we'll see a phase difference between the two orthogonal components N0 and Ne. And as delta phi, it depends on lambda. We'll see. We'll see. We can filter out what is the wavelength to be built up inside the cavity and what is the wavelength not to be built up inside the cavity. Okay. So these are the different modes of frequency selective feedback mechanism. So I think these are all clear to you. So let us move to what are the fiber lasers. So we'll quickly go through the week 11 concept and after that we'll solve few problems that is related to week 10. Okay. In each section, I will solve few problems that is related to the previous week. So why fiber laser? So if you want to find out the reason, so there are different advantages of using a fiber laser. One being high efficiency of the fiber laser due to low quantum defect. So if you recall one of our previous live session, so we have seen what is the quantum defect. So and for the fiber laser, the quantum defect it is less than 0.2 in it will be a mean DFL. The next advantage is the very good beam quality, which is close to the diffraction limit and square equal to 1. And least thermal problem due to the large surface to volume ratio because we use circular core fiber, which is large surface area to volume ratio. So this will lead to least thermal problem. And compact footprint means compact dimension. Footprint means dimension. So compact means we can integrate various components inside the fiber laser to make it more compact. And it is so as we have seen, it is integrated fiber optics design with very less mechanical misalignment, and we can design various type of fiber laser, which is one is Q switched or continuous wave or mode lock for mode locked operation. And high output power is also possible in continuous wave mode and long maintenance free lifetime, which is around 10,000 hours and several lasing wavelength tuning range. If you see, this is in the order of 100 nanometer and this is also in the order of 100 nanometer. So this tuning is only possible using fiber laser and this geometry is compatible with optical fiber system or application. So these are also some information about comparing the fiber laser with the India glam pump laser or diode pump solicited laser or diode laser. So if you see the efficiency of this fiber laser is around 30%. So this efficiency is the wall plug efficiency that is P output divided by P electrical. Okay. If you compare it to the India clamp pump laser, it is around 4%. And if you compare it is to diode pump solid-state laser, it is around 12%. And for diode laser, it is around 40%. Okay. And the output power in the multi-mode operation, it is of the order of 100 kilowatt. And for single mode operation, it is on the order of 10 kilowatt. And for NDF, which is flash lamp pump laser, it is in the order of 10 kilowatt. And for diode pump solid state laser, it is 6 kilowatt. And for diode laser, it is 10 kilowatt. And if you compare the lifetime, it is comparatively larger than the other lamp pumped laser or diode pumped solid state laser. So the lifetime is in the order of 100,000. So it is on the order of 1 lakh. And for the lamp, it is in the order of 600. For diode pump, it is on the order of 10,000. And for diode laser, it is 10,000 for the pump, 808 nanometer. Sorry, 10,000 for the laser wavelength, 808 nanometer. And 1 lakh around 980 nanometer. And for cooling, you can use air and water for fiber laser, similar to lamp pump, which use water for cooling. Also, for diode pump solid state laser, it requires water, or diode laser, it requires both either air or water for the cooling system. And maintenance, if you see, this fiber laser require very low maintenance, so it is highly feasible for various applications. If you compare it to the lamp pump system, which is NDAG and diode pump solid state laser, this requires higher maintenance. So often you require high maintenance for the proper operation of this laser system. So that is why fiber lasers are more economical and more convenient to use for getting a laser action. So the next one that we'll see is the fiber laser. What are the different components of fiber laser? So if you see, it consists of one active medium, which is often the rare earth doped optical fiber, and one optical resonator cavity, which is formed by dichroic mirror or fiber Bragg grating, reflecting at the required wavelength, and pump, which is laser diodes of appropriate wavelength and power to excite the active medium. So similar to a diode pump laser or flash pump laser, it consists of three components: active medium, optical resonator, and pump. So if you see the schematic, the diode laser. So if you see the schematic, 1 minute. If you see the schematic, it consists of a diode pump, diode laser pump, which is focused through a lens to the dichroic mirror, a mirror M1 and mirror M2. And the active medium is a rare earth doped fiber. Okay. And to make it more compact and rock device, the mirrors M1 and M2, you can replace the mirror by a fiber pigtail laser diodes. Sorry, you can replace the mirror by fiber Bragg grating, which provide high reflectivity to certain wavelength and very low reflectivity to the other wavelength. Okay, so we can replace the mirror by fiber Bragg grating, and we can replace the pump by a fiber pigtail laser diode. Okay, so instead of focusing the diode laser pump through a lens, what you can do, you can directly use a laser diode, and a fiber is coming out of this laser diode to excite the active medium. So this is the schematic of a fiber pigtail laser diode. Okay. So now we'll see some of the common example of fiber laser. So first one being is the erbium doped fiber laser. So if you see, it is consisting of similar to a fiber. It consists of two layers. One is the inner core, which is this region, and a outer cladding. And the core layer, it is doped with erbium ion, which is a concentration around 40 to 400 parts per million. And the absorption, absorption at 980 and 5050 nanometers. So 980 is around 5.5 dB per meter, and 1550 is around 5.2 dB per meter. So if you recall, the guided mode, that is the laser wavelength, it is guided along the core of the fiber in terms of the Gaussian mode. This is the fundamental mode of a fiber. And the fiber, the laser wavelength, it similar to this Gaussian distribution, it propagate along the core of the fiber. And the numerical aperture of the fiber is around 0.2 to 0.3. So if you recall the numerical aperture, it defines what is the maximum angle up to which the light will be guided along the core of the fiber. So if you incident a light in the core, you can make up to certain angle, it will be guided along the core, and beyond this angle, it will not be guided along the core. So this defines, the sine of this angle defines the, sine of this theta angle defines the numerical aperture of the fiber. And cutoff wavelength is around 930 nanometer, and the mode field diameter is around 5.5 millimeter at 1550 nanometer. Okay. So this is the schematic of a erbium doped fiber amplifier. So if you recall, this we have seen earlier also. So we combine the pump, which is 980 nanometer, and the signal, which is 1550 nanometer, through a WDM coupler, wavelength division multiplexing coupler. And this coupler, it efficiently couple the pump wavelength as well as the signal wavelength to the erbium doped fiber. Okay. So the green region here is the erbium doped fiber, where we see building of laser wavelength due to the population inversion inside the medium and the stimulated emission of these excited atoms. So if you see, this is the weak signal which get amplified in the output. And you can use this erbium doped fiber amplifier as a laser system also. If you put mirror here and mirror here, then this also act like a fiber laser. Okay. So this is the schematic of the energy levels of erbium ion. So if you see, this is a three-level system, which is the ground state energy is A1. The first excited state E2, which is the metastable state, and one is the E3. So when you pump the active medium, the erbium ion, it get excited to the higher energy level, and from the higher energy level, it get de-excited radiatively or non-radiatively to the metastable state. And from this state, they get populated for a longer interval of time. And eventually, when you put a signal of 1550 nanometer, it will get de-excited to the ground state, and it will emit radiation by stimulated emission. Okay. So this we have seen earlier also. And typically, what do we use? So as I've said earlier, instead of mirror, you can use fiber Bragg grating to reflect to replace the mirror. so that we can make the fiber laser more compact. So if you see, so this is the schematic of a fiber, which consists of a glass core and glass cladding of refractive index N2, core is refractive index N1, and a plastic jacket layer which provides a support to the system. And besides this, you can see there is a periodic change in the refractive index in the towards the end of the fiber. So this is what we mean by fiber Bragg grating. So similar to the Bragg's law, we can see there is a condition of getting a reflected strong reflection from this fiber Bragg grating. So if you see this equation, which is outlined by this red colored box. So the condition is lambda r equal to 2n effective gamma. So let's say gamma, it is gamma. So this lambda r is the wavelength of the reflected light, n effective is the effective index of the grating mode, and gamma, it is the separation between the grating. This is the periodicity of the grating. So whenever the wavelength satisfies this condition, this wavelength of light will get strongly reflected from the fiber Bragg grating, and other wavelength of light will simply pass through this fiber Bragg grating. So you can see this also acts like a mirror, reflective mirror. So in terms of the spectrum profile, let's say we have a spectrum like this. So this is the spectrum. This is a broad spectrum where we are seeing high intensity around this range of wavelength. And if you use a fiber Bragg grating, we'll see there is a dip here. So the dip corresponds to lambda r. This satisfies the Bragg condition, which is equal to 2n effective gamma. Okay. So by using fiber Bragg grating, which is FBZ, you can selectively reflect the wavelength which you want to build up inside the fiber laser and transmit the other wavelength through the fiber Bragg grating. So in erbium doped fiber laser, what we can do? So we have used mirror M1 in terms of fiber Bragg grating 1 and mirror M2 in terms of fiber Bragg grating 2. Okay, so this is 98% is reflectivity around the reflection wavelength lambda r, and it is 40 to 60 reflectivity around the wavelength lambda r. Lambda r is nothing but the laser wavelength which is getting built up inside the fiber, erbium doped fiber. Okay, so this is similar to the earlier schematic, that is we use 980 nanometer pump and the signal 1550 and couple through this WDM coupler and pass when you pass through this FBZ, what will happen? The 980 nanometer, it will easily pass through this FBZ1, but the 1551 will get reflected towards the input. Okay. So when this pump it get passed to this erbium doped fiber laser, it will excite the erbium ions in the silica matrix, and it will satisfy the condition for population inversion, which is delta n greater than 0. And when this condition is satisfied, we'll see a building of laser wavelength inside the erbium doped fiber. And this wavelength, when it passes through this FVZ, the 1550 only around 40 to 60% of the 1550 nanometer will get reflected and other will pass through this FBZ1, and the 980 nanometer pump will easily get this BZ2. Okay. And to separate the pump, the unused pump from the signal, the laser output, we can use WDM coupler, which efficiently decouple the 980 nanometer wavelength as well as the laser output. Okay. So this is the schematic, this is the profile, the laser output profile of a practical laser system, erbium dope, which is erbium dope fiber laser. So if you see below threshold, there is no amplification. So whatever response we are getting, it is due to spontaneous emission. And above threshold, you see these there are various longitudinal modes that is in the output of the laser. Okay. So this wave clearly seen in our previous lab session. So to decouple this longitudinal modes, what you can do, you can use etalons to decouple this longitudinal modes. And you see this lasering action is happening around 1530 nanometer. Okay. Other than this, so let us move to our next part. So in previous laser system, we have seen only one pump is used to excite the active medium. So instead of using only one pump, you can use two pumps to excite the laser system, to excite the active medium simultaneously. And this you typically use this for to get high power laser. Okay. So this is the schematic of using two pump system. Okay. So so the laser from the diode is focused through this mirror, and so these are the dichoid mirror, mirror M1 and mirror M2, which has highly transmittivity for wavelength around 976 nanometer and high reflectivity for wavelength around 1600 nanometer. So what will happen whenever this pump incident on this active medium, we'll see the lasing action being happening in this erbium doped fiber around 1600 nanometer. And you can easily see this mirror M1, it is slightly tilted so that some part of this laser output is being extracted from the system. Okay. So you tilt the mirror M1 so that you can get the laser output. So this is using double pumped erbium doped fiber laser. And so this is another type of fiber laser where you use double clad rare earth doped fiber structure to get high power laser. So to get high power laser, what you do, you inject the pump, which is around 976 nanometer, inject the pump in the inner cladding. Okay. And the core and the pump wavelength, they propagate separately in the fiber laser. So the signal, which is the laser output around 1530 to 1650 nanometer, it is propagating in the core layer, and the pump, it is propagating in the inner cladding layer. So this is the double clad fiber. Um, you have inner core layer where you use rare earth ions to dope the system for the doping. And you use two types of cladding, one inner cladding and one is outer cladding. And you inject the pump signal to the inner cladding so that the guiding mode in the core and the pump wavelength, they do not interfere with each other. So this pump wavelength and the lasing wavelength, they propagate separately in the separate region. And if you see the schematic, this figure, the inner core layer, it is very thin, where the laser wavelength is propagating. The inner cladding, it is of the order of 400 micrometer, and the core is in the order of 10 micrometer. Okay. So double clad laser, it is used for to get high pump power. And because we are pumping the laser, we are using the pump in the inner cladding layer. So you can use high power of the pump wavelength to get a higher population inversion in the core layer. Okay. And this pump wavelength and the signal wavelength, they propagate independently in the different regions. So let us see our next part. So this is the some of the experimental result. That is the relation between the input pump power and the output laser wavelength. So if you see this follows, if you see the figure one. So the laser wavelength and the laser output power and the observed pump power, they follow a linear relationship. So as you increase the pump power, the output laser power is also increasing. And this is the spectrum profile. You are seeing the pump peak is around 976 nanometer, and you are seeing amplified peak, which is around 1600 nanometer, which is the signal peak. Okay. And these are some information about the erbium doped fiber. What is the fiber length? So, what is the numerical aperture? What is the input power? So, these are some information about the erbium doped fiber. So, let us see the next fiber laser, which is ytterbium doped fiber laser. So, this is used to get high power uh, ytterbium doped fiber laser, and these are typically used in military, aerospace industry, shipyard industry, for pipelines, or for remote cutting of large scale product, infill dock and concrete cutting, heavy industry for deep penetration welding and cutting, and drilling in gas and oil well. Okay. So this application require high power laser. So for high power laser, you can use ytterbium doped fiber laser. So let us see the details. So these are the absorption and emission cross section of a ytterbium doped germanosilicate glass. So if you see, there are two absorption peak. One is around 915 nanometer, when one is around 975. And there are two emission peak. One is around 975 and one is around 1035 nanometer. So these are the absorption cross section of the different wavelengths. So for 975, the absorption cross section is around 4470 Newton per minus 27 meter square. And for 915, it is around 792 into 10 to the minus 27 meter square. And for emission cross section, the sigma E for 975, it is around 4470 Newton to minus 27. And sigma E for 1035 is around 850 Newton to minus 27. So let us see the experimental configuration. So this is for single-ended pumping, where you use a fiber pigtail to couple the laser in the cavity, which consists of a dichoic mirror, consists of two dichoic mirror and one dichoic mirror, and one end of this erbium dope fiber, it is cleaved, and in this cleaved end, it acts like a mirror M2. Okay, so instead of using other dichoic mirror, you can use this cleaved end to act like a mirror M2. So this cleaved end, if you find out what is the reflectivity, the reflectivity formula, it is at the interface, it is given by N1 minus N2 divided by N1 plus N2 square. And for glass, it is 1.5. For air, it is 1. So if you calculate it, you will see the reflectivity is around 4%. So this also acts like a mirror M2. Okay. So this is for single-ended pumping. But for high power laser, we require double-ended uh, pumping. So instead of a single pump, you can see there are two fiber pigtail. One is this and one is this, around 975 nanometer. And these are used to pump the system, which is a erbium doped fiber. And there are two dichoic mirror, which is high reflectivity for the laser wavelength and high transmittivity for the pumping wavelength. And the second dichoic mirror, it is tilted at some angle so that some part of this laser wavelength will get transmitted in the output. This is the overall schematic of a high power continuous wave fiber laser using a double-ended pump. This we have already seen. So this is let me see. Okay. So this we have seen earlier also. This is the spectrum profile of a fiber laser output. You can see there is a pump signal around 975 nanometer and there is laser wavelength signal around 1093 nanometer. And what else? So this is done. And this is also we have seen the pump power, output pump power and the pump power, input pump power and the output power of the laser wavelength follows a linear relation. So they follow a linear path. If you see the figure, it follow the linear feed with a slope efficiency of 72.960%. Okay. And this is the schematic of a Q-switched fiber laser. So we have seen we can design the fiber laser either mode locked or Q-switched. So you can design different types of laser systems. So we have for bulky laser system, we have seen cavity dumping, mode locked system, and Q-switched laser system. So similarly, in fiber also, you can design a Q-switched fiber laser by using a acoustic modulator here. So it is this, you recall, it is fiber pigtail, where laser diode is it is attached to a fiber end, and this is passed through a acoustic modulator. Okay, so depending on the phase difference that is created inside the acoustic modulator, you can see we can switch the resonator, the quality factor of the lasing wavelength. And one of the dichoric mirror, it is tilted at one angle so that some laser wavelength it is transmitted to the output. So this we have seen earlier also. This is also the same we have seen earlier. This is the output spectrum profile of a Q-switched pulses from erbium doped fiber laser. Okay, and so let us move to the next part, which is tunable erbium doped fiber laser. So tunability is achieved by a tunable band pass filter. So let us see in details. So UAB pump fiber pigtail, which is around 980 nanometer. And this pump, it is coupled to the erbium doped fiber by a WDM coupler and through a weak signal, which is 1550 nanometer. And these two signals, it is passed through this erbium doped fiber where we see amplification of light. And this isolator, it acts like a filter which do not allow the backward movement of light to propagate, and it allows only the propagation of light in one direction. So this isolator isolates the propagation of light, and when the propagation of light it is passed through a tunable bandpass filter, what will happen depending on the band pass filter, the different wavelength of light will get filtered out in the optical spectrum analyzer. So if you recall the absorption and emission profile, so this is the absorption profile of a erbium doped fiber laser, and this is the emission profile of a erbium doped fiber laser. So you can see the emission is happening over a range of frequency, right? So the emission is happening over a range of frequency. So the output you get it from here, it's like you see a range of frequency that is get amplified in the erbium doped fiber. And when this is passed through a tunable bandpass filter, depending on the bandpass filter characteristics, only one of the wavelength will be filtered out through this bandpass filter, and some part of this output of this bandpass filter it is coupled through this tap coupler where 10% of light. So tap coupler, it acts like a mirror M2. So it couples 10% of light to the optical spectrum analyzer and 90% go back to the WDM coupler. Okay. So by tuning the bandpass filter characteristics, you can tune the you can filter out different wavelength of this erbium doped fiber laser. So if you see the output, power versus wavelength, you can see from 1525 to 15 around 1560, in between 1560 and 1565, you can see the power is nearly uniform. The pump, when the pump, this figure is for the pump power when it is 102 milliwatt. So this we have already seen earlier. So these are some of the advantages of using a fiber laser. One is high frequency due to low quantum defect. Other one is very good beam quality. Other one is least thermal problems due to large surface area to volume ratio and compact footprint with flexible fiber optics delivery. And this we have seen also in the next, now previous part. So this is the quantum defect formula. If you recall, this quantum defect is given by this formula h nu p divided by h nu L divided by h nu t. So in terms of wavelength, it is given by lambda p by lambda L. So when lambda p is 975, we get laser wavelength around 1064 nanometer. And if you find out what is the answer, it will be 0.81. And the quantum defect will be 1 minus lambda p by lambda L, which will come around 0.11. And for different types of laser, fiber laser will get different quantum defect. According to the fiber laser in the question, you can calculate what is the quantum defect of the laser. So next, let us see what are the semiconductor laser. So before that, so let us okay. So let us quickly go through few slides. Then we will solve the problems uh, that I prepared by using the week 10 concept. So the semiconductor laser, it is invented in 1962 by four different groups almost simultaneously. And the advantages of the semiconductor laser, first is it is compact, and so it is of small size. Next, it is highly efficient, and that is efficiency is in between 30 to 16 percentage. And next one is direct modulation, that is mm, you can directly modulate the tunability by changing what is the injection current. So if you recall, by injecting by changing the injection current, which is IOT, we can directly modulate the laser output. And a direct modulation of 10 gigahertz is also possible using the semiconductor laser. And various optoelectronic integration is possible when you use semiconductor laser. And the optoelectronic components is like you can integrate either waveguide, or you can integrate splitter or modulator or photodetector. You can integrate easily when you use a semiconductor laser. Okay. So the basic structure is it's a forward biased PN junction of a dielectric band gap material. So we don't use indirect band gap material for laser system, and indirect is used for LED, not for laser. So some of the examples of direct band gap material is gallium arsenide and indium phosphide. Okay, and this is the schematic of a laser, semiconductor laser. So you have a P-type semiconductor, which is sandwiched to the N-type semiconductor through a thin layer of active medium in between. Okay. So the dimension is it is around 300 micrometer in length, and it is 200 micrometer in width and 100 micrometer in height. So, and there are two cleaved facet, and this cleaved facet acts like a mirrors M1 and M2, which provide reflectivity to the oscillating laser wavelength. And the other two faces are socket of facet, so that there is no building of laser wavelength in this direction. So we only confine the laser wavelength in this direction. The laser wavelength get build up in this direction where cleave facet is present. And if you want to find out the reflectivity, so reflectivity, if you use the formula N1 minus N2 divided by N1 plus N2 square, and by taking N1 as 3.5, you can easily find out the reflectivity is around 32 percentage. Okay. So the reflectivity is around 30 percentage. And this is the device configuration of a semiconductor laser. So as we have seen earlier, it consists of a p-doped and n-doped semiconductor, which is sandwiched through a active layer. So if you see the orange shaded region, this is the active layer. So this is the active layer where the light get built up inside the inside the 1 minute. So sorry for the interruption. So if you see the device configuration, it's like a raised waveguide of double heterostructure laser. So if you see the schematic, there are p-doped semiconductor, n-doped semiconductor. This acts like a substrate, and there is a active layer, and this is the model spot of the laser that is being built up inside the active layer. And we use metal electrodes for current injection. And what will happen when we provide a current? So inside this active layer, the electron hole will combine through say, a stimulated emission. And because of this, we'll see a building of laser bubbling inside this active layer. And doping is required to minimize the electric resistance or uh, to increase the conductivity of the p-doped or n-doped sample. Okay. And this is the longitudinal cross section of the double heterostructure laser. Um, so if you see, so this top layer is the p-doped semiconductor. Orange shaded region is the active layer, and the lower region is the n-doped semiconductor. So this is the same figure. So where we've provided some dimension of the different layer. So let's say for the active layer, it is typically which is the orange shaded region. This is typically of the order of 0.1 to 0.2 micrometer, and this active layer is gallium arsenide, which is a low band gap material. We'll see why we use a low band gap material. And the next layer, which is p-doped aluminum gallium arsenide, which is typically on the order of 1 to 2 micrometer. Next layer is the next layer, which is just below the active layer. It is n-doped aluminum gallium arsenide. In the top one, which is adjacent to this metal contact, it is P plus gallium arsenide, and this one is N plus gallium arsenide. So this dimension is in the order of 15 to 60 micrometer, and this dimension it is in the order of 0.2 micrometer. So these are the longitudinal cross section of double heterostructure laser. So the heterostructure junction, if you want to know what is this heterojunction means. So heterojunction means the junction between dissimilar semiconductors. So typically for homojunction, we have same kind of material on either side of the junction. So if you combine a p-doped silicon with a n-doped silicon, this is termed as a homojunction. But adjacent to the junction, you have different types of materials such as gallium arsenide in one side and aluminum gallium arsenide in other side. Then we term it as a heterojunction. And double heterostructure means we have at least two heterojunction on either side of the eye gas. Okay, so if you see this figure, so the green shaded region, it is the active layer. So if you zoom it, so this middle region is the gallium arsenide, and the top one is it's the p-doped gas. In the lower region is n-doped gas. And there are two junctions. One is p-doped in between p-doped gas and gallium arsenide, and other one is gallium arsenide and n-doped gas. And the active region thickness is around 0.1 to 0.2 micrometer thick. And we use double heterostructure laser because it provides certain advantages over the single junction, such as the carrier confinement. So we'll see the gain, it depends on the carrier confinement, the carrier concentration. So that is why we use double heterostructure laser. And the optical confinement is it is more the laser wavelength that is building inside the active layer is more tightly confined inside this active region, and it provides lower losses and it provides a design flexibility. So these are some the main advantages of using a double heterostructure semiconductor laser. And this is the energy band diagram of a PN junction. So before contact, so if you recall the p-doped semiconductor, the Fermi level, it lies close to the valence band, right? So EC means the conduction band and EV is valence band. And for p-doped semiconductor, the Fermi level, it lies close to the conduction, just above the, sorry, valence band. And for n-doped semiconductor, the Fermi level, it is lies close to the and just below the conduction band. And EZ is the band gap between this conduction and valence band. EZ is typically given by EC minus EB. Now this diagram is just before the contact. Okay. So now when you have a contact, 1 minute. Okay. So when you have a contact now, so what will happen? This, due to the different concentration of ions, that is electrons and holes on either side of the junction, what will happen? The carriers will move to the next side. So electron will move from the n side to the p side, and hole will move from the p side to the n side. So what we'll see? We'll see a current. Whatever one is the diffusion current because of the carrier concentration, and one is the drift current due to the electric field that is being generated due to this building of ion on either side. Okay. And what will happen after some time? This current will balance with each other, and we'll see that the drift current and plus the diffusion current will be zero, and there will be a depletion region between this p and doped semiconductor. And at equilibrium, it is defined by a single layer of Fermi level, which is EF. Okay. So this is given by a single layer of Fermi level. And when you forward bias it, well, what will happen? So for forward biasing, we apply high potential to the P and low potential to the N side. So what will happen now? This voltage, and now this external voltage, it will allow the diffusion of electrons from the n side to the p side, and it allow the electron hole combination. So it typically uh, lowers the depletion region length. So the ions that is immobilized in the depletion region, that will now they will combine with each other, and because of this electron hole recombination, we'll see spontaneous emission or lasing action that is being happening in the active layer. And so in forward biasing, instead of one Fermi level, we'll see two Fermi levels, which are termed as quasi Fermi levels. One is Fermi level, valence band Fermi energy level, and another one is conduction band Fermi energy level. Okay. So at equilibrium, there is only one Fermi energy level, and when you forward bias it, we'll see a different Fermi energy level. One is conduction, quasi Fermi energy level for the conduction band, and for the valence band. So we'll see the next part in our next live session. So for now, let us solve few problems. So the question one says, in a passive mode locked laser using a laser, intracavity saturable absorber, the relaxation time of saturable absorber must be greater than or equal to cavity round trip time. So what will be the answer for this question? So if you recall for saturable absorber, so it should the relaxation time should be much smaller, so that it will get back to the higher higher lossy state after passing one lasing wavelength, right? So it should go back to the higher lossy state in a short interval. So that means the relaxation time of this saturable absorber should be smaller than or equal to the cavity round trip time. So that means this statement is false. So let us move to our next question. So question 2 says, which one of the following is not suitable to obtain a pulse laser output with variable pulse repetition rate? One is gain switching. The option B is external modulation. C is squeeze switching, and D is mode locking. So if you recall, in mode locking, it is not possible to vary the pulse repetition rate, right? So that means the answer is option D, which is mode locking. So let us quickly move to question 3. So question 3 says, a mechanical chopper is used to modulate the output of a continuous wave laser with an output power of 30 millivolt. If the modulated laser output comprises a train of rectangular pulses with a time period of 100 microseconds and 30% duty cycle, then what is the average output power of the modulated beam? So let us see what is given to us. So output of a continuous wave laser is given. Output power, it is given as 30 milli. And there is a train of pulses that is being generated by this mechanical chopper. So this is rectangular pulses. So this will have same width. So let us take one pulse. So it is rectangular pulses with time period. Time period is given. It is 100 microsecond. And the duty cycle is 30%. Then what is the average output power of the modulated beam? So the average power, it is given by total power into pulse width divided by time period, right? This is the average power. And you are given the duty cycles. So duty cycle, it is nothing but, so duty cycle, it is the ratio of pulse width divided by the time period. So that means this term here, it is nothing but duty cycle, right? So the average power will be is total power into duty cycle. And total power, it is given 30 milliwatt. And duty cycle, it is given 30%, I think. So it is 0.3. So that means the average power is 9 milliwatt. Okay. Let us see the next one. So the B part, it is asking what is the energy per pulse obtained at the output after the chopper is. So energy per pulse obtained at the output after the chopper is days nanojoule. Enter the answer as an integer. So the answer will be so for energy pulse per pulse, what you need? Energy per pulse is given by P average into time period. In P average, we have already calculated. In the first part, it is 9 milliwatt. In time period, let us see what is given. Time period, it is given as 100 microsecond. Is 100 microsecond. So that means the energy per pulse, it will be 900 nanojoule. This is the answer. So the next question is a multi-longitudinal mode gas laser of cavity length 25 centimeter is oscillating with 50 longitudinal modes. The ratio of peak output power in mode lock condition to the average power in random phase condition is. Assume that all longitudinal modes have equal amplitude. So this is similar to one of the problems in the assignment 10. So the output power in mode locked condition, it is nothing but n square I0 divided by the average power in a random phase condition is ni0. And n is the total number of longitudinal modes. So this will give n, which is 50. So this will be the answer. And it is also asking what is the pulse width of the output pulse in the mode locked condition. So if you recall, in the mode locked condition, the time period of the pulse, it is given by time period of pulse is T is 1 by nu f. So Tf equal to 1 by nu f. Nu f is nothing but C by 2nl, right? So this will be 2nl by C. So n, we can take it as a 1 because it's given refractive index of the cavity is 1. So 2 times length of the cavity, which is 25 centimeter, 0.25, and C is 3 into 10 to the 8 meter per second. And if you calculate it, you will get the time period around 1.66 nanosecond. And the pulse width, if you recall, the pulse width, it is given by delta T, it is Tf divided by n. So it will be 1.66 divided by 50. So which is around 33.3 picosecond. Okay. So let us see our next problem. So it's a conceptual problem. So question is asking, in a particular laser operating at a pump power above the threshold and giving continuous wave output power, one of the resonator mirror which provides feedback is suddenly removed. Which one of the following would occur immediately afterwards? So, so you suddenly remove a mirror, either M1 or M2 from the system, and the question is asking what will happen immediately afterwards. And the laser is already working above the threshold. So let us see the options first. So the first is output power increases and population inversion decreases. So this is not the answer because output power will decrease because there is no feedback now. Second option is output power decreases and population inversion increases. So this is the right option because when you remove the mirror M2, the output power will decrease because there is no feedback mechanism. So the building of laser wavelength will decrease over time. That means the output power will decrease and the population inversion will increase because whatever atoms that is there in the metastable state, they will not able to jump to the ground state because there is no stimulated emission. There is no wavelength that is earlier there um, to stimulate the de-excitation of the atoms from the excited state to ground state. So to stimulate the de-excitation, we need the feedback, right? That is why the answer will be option B, which is output power decreases and population inversion increases. So the next problem is it is also a conceptual one. So this means in a digital optical communication, the binary digit one it is represented by option A, sequence of laser pulses, a frequency modulated laser pulse, C, a laser pulse, T, a time modulated laser pulse. So if you recall, the binary digit 1, it is represented by a presence of laser pulse, and 0 is it is represented by a absence of laser pulse. So that means when if the binary digit 1 is there, that means there is a laser pulse in the optical communication. So answer will be C, a laser pulse. Next problem, it's a numerical one. So the question says a Q-switched Nd:YAG laser has a gain medium with a stored energy of 100 millijoule, and the laser emits a pulse with a duration of 20 nanoseconds. Calculate the peak power of the pulse and the energy density if the beam diameter is 5 millimeter. So let us see what is given to us. So it is given the energy stored in the gain medium is 100 millijoule and the pulse duration is 20 nanoseconds. So that means we can easily calculate what is the peak power. So peak power it is given by energy stored, pulse energy and pulse divided by pulse duration. And energy is 100 millijoule divided by 20 nanosecond. And if you calculate it, we'll get around 5 into 10 to the 6 watt. Is 5 megawatt. And the next part is, what is the energy density of the pulse? The beam diameter is 5 mm. So energy density energy density it is given by. So there is a lag of video and my voice. So please bear with this for now because there is a network issue in my area. So energy it is nothing but we want to find out the energy density. So let us see what is given to us. The pulse energy is given and area is also given. So that means energy density is given by energy, pulse energy divided by area. So this is 100 millijoule. Area is pi r square. 5 by 2 into minus 3 square. And if you calculate it, it will come around 5094.24 joule per meter square. So let us see the final problem. So in a cavity dumped laser, the round trip time of the cavity is 15 nanoseconds and the intercavity power builds up to 200 watt. If the efficiency of the cavity dumping process is 18%. Calculate the energy of the extracted pulse. So it is asking about how much energy will be extracted during the cavity dump laser. So what is given? Round trip time is given. Round trip time of the cavity is 15 nanoseconds. And the energy buildup inside the cavity is intracavity power is 200 watt. So that means energy stored during one round trip is energy stored in the cavity during one round trip is E into T, right? E is given 200 watt and it is 15 nanoseconds. And it will come around 3 microjoule. And the energy extracted depends on the efficiency. So energy extracted will be the energy stored during one cycle multiplied by efficiency. So this is 3 microjoule and efficiency it is given 0.8, which will come around 2.4 microjoule. So this is the answer. Okay. So we have solved few problems related to methane and we have discussed a few concepts, different types of laser that is being used. So we'll cover the next part of the semiconductor laser and week 12 concept in our next live section. So for now, thank you for joining the session. Although there are only one people that have joined the live section. So it's okay if but if you have any doubt, please feel free to write in the discussion forum. As well as you can also join the live section and you can ask the doubt at any time. So please feel free to stop me at any moment and ask your doubt and clarify your queries. Okay. So we'll meet on next Saturday, same timing from 4 to 6 to discuss the remaining part of semiconductor laser and to solve few problems that is related to week 11 concept, as well as I will try to clarify the doubts of weekly assignment. So let us end the section and let us meet on next Saturday. So bye everyone.